So I think maybe we can get started. Good morning, everyone. This is Chang Du from Columbia University. It's my honor and pleasure today to chair the SIAM von Karman Prize lecture. This prize was established in 1968 to honor Theodore von Karman and his work in aerodynamics. The prize is awarded every 5 years for notable application of mathematics to mechanics and or the engineering sciences made during the past 5 to 10 years preceding the award. This year's, the 2020 prize recipient is Kaushik Bhattacharya, the Howard and Tyson Senior Professor of Mechanics and Professor of Material Science and Caltech. Kaushik received his bachelor degree from IIT Madras, India, and PhD from the University of Minnesota. Before joining Caltech in 1993, he was a postdoc at the Krohn Institute. His research concerns the mechanical behavior of solids and specifically user theory to guide the development of new materials. His many honors include the Distinguished Alumni Award of IIT Madras, Outstanding Achievements Award from University of Minnesota, the Walter K. Coiter Medal of ASME, and Graduate Student Council Teaching and Mentoring Award at Caltech. He served as editor of the Journal of Mechanics and Physical Solids from 2004 to 2015. Let me add that Kaushik is also the current SIAM Material Science Activity Group Leader, Group Chair. Let me also read the official prize citation. The 2020 Theodore von Karman Prize is awarded to Kaushik Bhattacharya in recognition of his major mathematical and computational contributions to material science. Let's congratulate Professor Bhattacharya and welcome him to give the prize lecture titled Mathematics, Mechanics and Materials, the Case Study of Liquid Crystal Elastomers from, very fittingly so, Caltech's von Karman Conference Room. Kaushik, it's yours.
Thank you very much, Chang. It is really it's humbling to be recognized, and it's really an honor and a privilege to be able to speak. I wish I could have done this in person, but I'm delighted that I'm able to do so from the von Karman conference room and museum on our campus at Caltech, with a bust of von Karman looking over my shoulder and many of his instruments and papers behind me. So I'm going to begin by, so I'll start sharing my screen. I hope you can all see the screen. Good. So I'll begin by recalling some of the earlier works of von Karman. And while we often think of von Karman in the context of fluids, he actually studied solids as well. And one of his earliest papers concerned the buckling or the instability of long, slender columns subjected to compressive loading. Here's a paper where he's trying to understand, describe the failure of marble and other rocks, again, columns subjected to compressive loads. And here's a paper again from the same period where he actually proposes what we now call the Pople von Karman plate theory. So when you see these themes, you see the themes of structural instability, the ability to describe the behavior of engineering materials, and you see a very early view of a multi-scale thinking because he's trying to understand the microscopic structure of this material before and after deformation. And you see the trying to build models which can be used for engineering problems, and in the context of plates in this case. So in many ways, the themes I'm going to talk about today resonate with these. But these days, we not only are interested in structural instabilities, but we are also interested in trying to understand material instabilities and the combination of structural and material instabilities. We are, of course, interested in developing effective theories but we do so with a very careful analysis of multiple scales. And we are interested not only in descriptive theories, but also theories which will allow us to develop new materials and improve new materials, and theories which will motivate new applications. Of particular concern today, I'm going to be interested in what I call functional or active, or some people call smart materials, where you're trying to combine a response of the material to multiple stimuli. For example, you're trying to combine electrical and mechanical, thermal, optical, and other properties into one material. You're also trying to make very sensitive materials so that you have large response to stimuli, or so that you can sense and actuate. And all of this is part of a larger program, which I call Material as a Machine, where you're trying to build enough functionality into the material so that the material itself can act as a machine. And I'm going to argue that one way of developing functional materials is to exploit phase transitions. All of us are familiar with steam, water, ice phase transitions. But what I want to point out is that there are a lot more phase transitions. And in fact, even in the solid state, phase transitions are actually very, very common. And so let me tell you why that is, and then try to go from there. Typically, atomic systems are discrete. Matter is discrete. And if you have a discrete system with a very large number of degrees of freedom, it's very common that you will have lots and lots of local minima or metastable states. And in particular, for example, in a liquid crystal, you might have a disordered state and an ordered state where most of the molecules are aligned in one direction. Typically, the low energy states are also the ones with low symmetry, because you basically are looking for very specific interactions to enable this low energy. Whereas the high symmetry phases typically have low entropy because of the fact that their symmetry is higher. So when you look at the free energy, which is a combination of the internal energy and the entropy, and you plot this as a function of temperature, you find that typically the high symmetry phase is stable at high temperatures, and the low symmetry phase is stable at low temperatures with a phase transition. Of course, this is a very simplified heuristic picture, but this is why you see lots and lots of phase transitions in nature in solid structures. What phase transitions also mean is that the energy landscape, which governs this, I've just plotted free energy as a function of temperature. I could also plot it as a function of a state variable or an order parameter which describes the state of the material. And if I did that, you find that the energy landscape is extremely non-convex, with a high symmetry phase being metastable at some temperature like this, and maybe multiple low symmetry phases with lower energy. So you have this extremely non-convex energy landscape. And so what that allows is that if I apply a small stimulus, I can easily move from one low energy state to another. And that is the reason why phase transitions on this complex energy landscape is a very natural way of obtaining functional behavior. But if you want to study these, you have to recognize that this non-convexity will also give rise to material instability. And you're really interested not only on the onset of the instability or bifurcation, like von Kármán was, but you really would like to understand deep into the post-bifurcation behavior. So you have to be able to develop tools which allow you to study deep into this unstable regime. And the second point, and the final point I'll try to make, is that we'll try to combine these material instabilities with structural instabilities so that you get a very complex situation. With that kind of broad overview, I want to so maybe one more slide, a little bit of mathematics. So if I try to minimize the energy of a non-convex energy, so let's look at this simple problem. It's a one dimension. I have some functional, which is a function of u and u prime. The integrand is u square, and something which is non-convex, being 0 at -1 and 1 in the gradient. So it's actually very easy to see that it's not possible to find a classical minimizer in any Sobolev space. You can't simultaneously make u equal to 0 everywhere and u prime equals to ±1 everywhere. And therefore, it's very easy to convince yourself that this integrand is always strictly positive. However, I can construct a sequence of functions which exploits the fact that the energy is 0 at gradients -1 and 1, but gradually approaches u equals 0 to construct a sequence whose energy goes to 0 in the limit. However, the energy can never be 0, so you really don't have a minimizer in a classical sense. And the reason is that these minimizing sequences develop finer and finer oscillations. And that's a mathematical manifestation of what you see in materials by fine scale microstructure. As you can see in the case of martensitic materials here, liquid crystals here, and liquid crystal elastomers here. And so there are multiple tools you can use, and a lot of them were developed in the context of martensitic phase transitions about 20 to 30 years ago, but we can apply them in many, many different fields. The one is trying to characterize the oscillations. In this sequence, you find that the gradients really take values plus and -1. And so the limiting distribution of the gradients is described by a probability measure of 2 Dirac masses, 1 at +1 and 1 at -1. The second, you can study the relaxation. So this was your original non-convex energy, but after forming microstructure, the behavior is guided by this red curve. So we'll call this the relaxed energy or the quasi-convexification. And you see that this has a large region where the energy is flat. So this is a region where you can very quickly change behavior. So you see that relaxed energies typically have a lot of soft behavior, even though the underlying material itself is hard. The other thing you could do is to say that when you build models of this nature, you're missing some physics which describes the interfaces. So you can try to either put in that physics or try to regularize this problem. And this enables us to try and do simulation at some great detail. And there's a deep connection, of course, between these two, that the regularized energy, as this regularization term goes to 0, the minimizers of this converges to the infima of this converges to the infima of this. So we characterize this by using gamma convergence. So these are the tools we use, and I'm going to repeatedly use this theme in multiple examples. And you see that there's a close connection between materials, the mathematics, and the mechanics underlying these materials. So let me describe the case study I'm going to do, one of liquid crystal elastomers. So let me break this out with first talking about liquid crystals. So these are large rod-like molecules, stiff rod-like molecules, and at high temperature, they are disordered because there's a lot of entropy. But at low temperatures, the steric interactions align them, so you end up with an overall alignment in a certain direction. So this is an isotropic fluid, but when you cool it down, it becomes kind of a murky liquid. So hold that thought. Let's now talk about elastomers. These are rubbery solids. And these are made out of a large number of polymer chains, long floppy molecules. These are typically liquids. But when you cross-link them, so think about old spaghetti. So now it acts as a solid, but it's a very soft solid because all of its elasticity comes from the entropy rather than the internal energy. So liquid crystal elastomer is a combination of these two, where you create polymer chains with this nematic mesogens. So notice that this is, though I draw it like this, these are really a molecular picture. This is only 2 nanometers. Each mesogen is about 2 nanometers. So there's enough free volume that these mesogens can still undergo their isotropic to nematic phase transitions. But as they do, they take the polymer chains along with it, so the solid actually changes shape in a dramatic way. And the result of this is that as you change temperature in these materials, you find that there is a very large change of shape, as you can see in this movie, hopefully. And again, this is kind of the measurement of this. This is temperature versus the stretch. And you can see the stretches are huge, factors of 2 and 3. The modulus of these materials are of the order of 1 megapascal, maybe 100 kilopascal. So the work that is capable that this small piece of rubber is doing is actually extremely large. It's 10 to the 5 joules per meter cube. And that's comparable to the best actuator materials, and in fact is comparable to what you get from hydraulic machinery. So though this is a soft material, this can be a very powerful actuator. The other aspect is one that you see here, is the soft behavior. If I take a piece of this rubber, which is prepared in a particular way, and pull in this direction, you find that the stress versus stretch behaves in this way. If you pull in a certain other direction, you find that you have the usual rubber-like elasticity, but transverse to it, you find very soft behavior. Here I describe the behavior with respect to temperature, but you can induce this phase transition using light, electric field, and other stimuli by preparing the material appropriately. So let's try to, and that's what I wanted to show, that this is an old experiment of Ikeda, where he puts in photoactive azobenzene into these materials. You shine light, it begins to curl up. You shine light of a different frequency, it comes back flat. And the fact that if you change the polarization, the actuation angle changes shows you that the actuation is directly by coupling to light rather than light heating up the material. So this is what I want to describe. This is the kind of behavior I'd like to try and understand and build models for. But one more piece of material science before I move on. And that is, I told you that these materials were made by a combination of liquid crystals and elastomers, by cross-linking polymer chains with liquid crystal mesogens. And so I have a choice at what temperature I'm going to cross-link my material. So I start off with the liquid. It's isotropic at high temperature, nematic at a low temperature. If I cross-link it in the isotropic state, I end up with what I call an isotropic genesis material. And you will find that this material behaves in a soft way and has applications for changing shape and for draping, shape conforming. Whereas if I were to start again with the liquid, but now cool it down to a nematic state and then cross-link, you find that this material is very stiff. It has no soft behavior. But by patterning the way the nematic is done by using liquid crystal technology, I can use it for shape actuation and shape morphing. So let me begin by describing the isotropic genesis material, and there I'll kind of go through the entire story and only talk about glimpses here, and then come back and talk about photo actuation. So starting with the statistical mechanics, Mark Warner, Eugene Terentiev, and their students developed a elasticity type theory for these. So I have 2 state variables here. One is the deformation gradient, which describes the stretch, and one is the director. And these materials typically have some disorder, and that I will describe by N0. So this is a frozen state which describes some state of the material. So there are three terms. One is basically the entropic elasticity of the polymer chains. It has some shape like this. One which is related to this kind of built-in frozen and fluctuations in the material, and that is this so-called non-ideal term. And the second, and the third, finally, you have the liquid crystalline elasticity, the Frank elasticity, and that's basically the spatial gradient of n square in a certain approximation. And this is the energy that you're trying to minimize under the constraints of incompressibility and the fact that your director is a unit vector. So it turns out that these two numbers are small. So the early part of the theory was done with what was called ideal materials, where alpha and kappa were negligible, were neglected. And what I'll show you is that in this case, this energy, even this energy is actually extremely non-convex. So let's look at that. So what I'm going to do is to define an elastic energy, which depends only on the deformation gradient, by minimizing this director out. So that's a minimization that you can actually carry out by hand. And what you find is that the ground state of this is a set of states where this F transpose L inverse F is actually equal to identity. So it turns out that it has a lot of ground states. And if I were to think about it physically, it means at high temperature, if I took a cube, when I cooled it down, it would become a rectangular cuboid. But it can elongate not only in one direction, but in multiple directions. And these are all possible ground states. So the energy somehow looks like this. It is zero on this entire manifolds of shapes, and it grows away from it. And consequently, you can very easily show that this is not convex, and in particular, it's not rank 1 convex, which is. So what that means is that I can take two states and make a state which has one part of it is in one state, the other part of it is in the other state, and the deformation remains continuous, or the deformation remains compatible across this interface. What that allows me is not only to have these ground states, but additional ground states. And basically what I'm doing is doing a relaxation by creating fine scale oscillations in this material. And this is what you saw manifest itself in this soft behavior that I described. So this material was created by Finkelman by making all the directors lined up here. So it's uniform. And the signature of this is that this material is translucent. When I start pulling in this way along this direction, this director wants to reorient and become horizontal, but as it does so, it tries to shear the material. And of course, the grips don't allow it. And therefore, what you find is half of it goes one way, the other half of it goes the way, creating this fine scale structure, which makes this material cloudy. And then when it's all aligned, it becomes translucent again. And this is the kind of soft behavior that you behave. So if I were to go back here and say, what is the effective behavior in one of the really remarkable results in this field, Antonio Di Simone and Georg Dolzmann were able to actually compute exactly the relaxed energy. This is one of the very few examples where you can explicitly compute the entire free energy relaxation. And this was done by the usual technique of finding upper bounds by doing particular constructions and then using some theory to obtain a lower bound. So about 10, 15 years ago, the belief was you have to either very carefully make the material, because in order to get the soft behavior, you had to make the non-ideal term non-zero. So what happens in ideal terms when you have a non-ideal material? So I can no longer compute. So now I not only have a non-convex energy, but I also have a heterogeneous energy because this N naught is not uniform. It's actually a fluctuation and hence random. So what you have is a material which is extremely heterogeneous. So what I can try to do is to compute at least the homogenization of it, the effective behavior. So I take a box of this material, I calculate the average, I impose an average shape, and I calculate the minimum of the average energy. Of course, I can't compute this explicitly. So one thing I could do is to compute bounds. And alpha equals 0 gives you one bound. And then, of course, you have the other bound. You have to do some theory. And again, you use what are called these polyconvex functions. You try to create basically test fields in the, you try to use known things and try to impose constraints in some relaxed way, and that gives you an upper bound. It turns out when you compute these lower and upper bounds, the upper bound is the dashed blue line, the lower bound is the red line, and you find that these are actually extremely, extremely tight. And in fact, these are the experiments. So you can take you can compute the bounds and use the fact that the stress-stretch relation has to be monotone and obtain bounds on the stress-strain behavior. And that's the theoretical bounds. And then the circles are actually the experiments. So you can see that one, the bounds are tight and show you that you still have soft behavior. The red line is the result of some simulation, and it turns out that you see that it does very well. And so by doing the simple bounds, you can understand that even if you don't have, ideality, that is, you have a non-ideal material, polydomain with lots of these fluctuations, you can still retain this soft behavior. And that makes it much more, these materials much more attractive for application, because now you don't have to go through this very complicated process by which you try to get rid of this term. So that's a use of theory to try and motivate a new way of making these materials. So one of the ways we use this material is in thin films. So let's try to think about trying to derive effective theories for that. So suppose I have a thin film of this material. So the domain is omega times 0h. This is the energy. So this is a three-dimensional problem. So what you'd like to do is to develop a simple, see whether you can exploit the thinness to make a simple 2D theory. And that's what we call a membrane. But you have two small parameters. You have the thickness, but you also have this kappa, which is a small parameter. So you try to do asymptotics using gamma convergence when both these go to 0. And you find that in the gamma limit, the effective energy behavior is described by the 2D theory, where the 2D energy, so all that matters is the deformation of the midplane. And you can obtain the effective behavior by basically from the 3D behavior by only looking at the first two columns and minimizing out the third column. So in engineering, we call this plane stress. Okay, but that introduces some structural instabilities, one of wrinkling, and then you relax against it and you get the effective behavior here. One of the things that is really remarkable is that this limit is independent of the ratio between these two small parameters. And second, we can compute this explicitly, and that's what I'd like to describe in a second. So if I take, so I'm really interested in the behavior in the plane, so I can describe it by looking at basically the in-plane metric and its two eigenvalues. lambda little m and lambda m. So it's convenient to actually look at the larger of these so-called principal stretches and the aerial stretch, which is the product of these two. And you find that this is what the energy landscape looks like. There's an explicit formula, but I'm going to describe the behavior in a certain way. There's a region where you have a structural or wrinkling instability, and there the state of stress is necessarily uniaxial tension, even though you have stretch in two directions. The stress in one direction is necessarily zero. Then there's a second region where you have fine scale material microstructure analogous to the stripe domains that I showed you earlier. And there the state of stress is necessarily equibiaxial tension. In other words, you have no shear stress despite the fact that you have shear strain. So here you have a solid, but because you have microstructure formation, it behaves like a fluid in this region. And there's a region where it behaves like a solid. So this is often what is called, this is known in even rubber-like materials, and it's often described using what is called the tension field theory, because you only have uniaxial tension. This is the new regime that this material offers. And so let's try to see whether you can probe this regime using experiments. And I'm going to describe a collaboration with Kenji Urayama. They built a biaxial machine so that they can stretch in two directions. And what you try to do is to stretch in all of these directions so that you have basically going to this region of equibiaxial tension. So these are the experiments, and you see that here you have the stresses in two directions, both the x and the y, and you see that the stresses always agree as we had predicted according to the theory. So this very simple theory, which you can compute explicitly, describes this behavior. Of course, you don't describe the lower part of this behavior because you have made some approximations to obtain this theory. So to describe the full behavior, we go back to our original energy with all the non-ideality, and you can do phase field simulations of these. And here's a case of planar extension. You see how the microstructure is evolving, and you see the state of stress. So here you're seeing both the computed one and the experimental one. This is both the computed one and the experimental one. And you see that you can actually, with just 5 parameters, describe a whole range of behaviors very well. What you're seeing here is the Young measure. So it actually tells you the distribution, some average, the statistics of the distributions of the directors that you're seeing here. And so here's some more comparison. So with actually just with 5 parameters, you're able to describe a whole range of experiments which were done with this material. And you can also, by using X-ray scattering, probe the distribution of the directors, and you see that this is the experiments and this is the simulations. And again, you get a very, very good understanding, good agreement between these two. Okay, but simulations like this also give you insight into how the overall microstructure is evolving, and you can use that to build engineering models. In engineering, you can't describe material behavior at each point with this level of complexity, so you need a very simple model, and it turns out that you can build this model in this way. What the simulation shows you is how this microstructure evolves, and use that to understand what is the elastic distortion of the matrix with all this complicated behavior going on inside. And what you find is you can describe this with 2 parameters, which we'll call lambda and delta. And so you have, this is basically elastic distortion of the matrix. This is behavior of some kind of internal stored energy in the microstructure. This is some latent heat because of the phase transition, and this is specific heat. You also need some evolution, so you have some dissipation, and you describe that some viscous behavior using dissipation rate, and we just use basically linear kinetics here. So these are your governing equations. You can calibrate these with experiments in macroscopic specimens, implement them in commercial finite element codes, and here's the validation. The dashed lines are the behavior of the model, and the solid lines are the behavior of the calibrating experiments. All these experiments are really calibrating only about 9 constants. So what we're able to, so you can do complicated engineering calculations now with all these complicated behavior built into it. And one of the things that you can study is a lot of different structural instabilities, including cavitation, a balloon instability, torsional instability. And in all of these, you see this very interesting combination of this material instability manifested by microstructure and structural instabilities that we know in structures. So here's an example where we can start really with the molecular theory and pass all the way to an engineering model by using statistical mechanics to get passed from the molecular theory to a mesoscale continuum theory. I didn't describe this. What I did describe is this part where you use a combination of explicit results and phase field simulations to gain insight, and then use that insight to improve the behavior of these materials. So I'd like to take a minute to talk a little bit about numerical methods, because the simulations I showed you can be quite expensive. You have an internal variable, you have elasticity going on. So, and this is something that you find in a lot of very different continuum kind of solid models. So the typical model looks like this. You have the deformation, you have an internal variable, you have some kind of equilibrium or dynamic equation, and then you have an evolution equation for your internal variable. So in our case, the internal variable was the director. Now the difficulty is, of course, this is spatially second order, nonlinear. This is first order in time. Finite elements is what solid mechanicians have been using for a long time. They work very well, but it turns out that they are very difficult to parallelize in extreme ways. You can parallelize, but you still need a lot of communications. And with the emerging platforms where you're using GPUs and other accelerators, it's very hard to implement it. Not impossible, but simply very hard. What you recognize is that despite the fact that these are nonlinear equations, they're actually composed of simple linear equations, your balance laws, and local nonlinear constitutive equations. So you can ask whether I can split these equations up in a particular way. And that is what we tried to do. So one way of doing this is the following. You take these governing equations, you discretize in time, and you try to do an implicit update. That, of course, has a variational principle. The difficulty here is that you have a gradient here. So you have to, typical way is you try to use finite elements to build in this gradient structure. Suppose I don't do that, but I actually introduce the gradient structure using a Lagrange multiplier. So I minimize over all matrices F, but then insist that F be a gradient. That's hard to implement numerically, so I put an quadratic term and augmented Lagrangian. So in some ways, this is a mixed method, but not quite, because I actually do have, and then I can try and use some kind of alternating direction where I minimize over F, I minimize over U, then check for, update my Lagrange multiplier, go on, so forth. What you notice is that this is always a completely local update. Not only that, you only need to solve this up to some LP norm, so only up till some processes, not in every point. This is a differential equation, but it's a nice operator. It's a Laplacian operator. So if you have periodic boundary conditions, you can use some kind of Fourier transform method. Otherwise, you can use other methods because on a structured grid. This is again local. So all of this becomes very, very amenable to applications in accelerators, and that's what we do. There's also deep connections between each of these steps and the underlying physics, but it turns out while we have good numerical analysis for the discrete problem, we actually do not have an analysis and convergence proofs for every step of the continuous problem. And that's an interesting problem because you have, it's a very interesting math problem, and that's one of the things that we're working on. But here's some numerical evidence of convergence, strong scaling and weak scaling. And this is where you go from one node to multiple nodes on a GPU machine that you begin to have a little increase, but then again, it stabilizes. So that is a little diversion on the numerical methods. So I thought I'll also have time to talk about Pneumatic Genesis. Given the time, I'm going to skip over it, other than mention that that has turned out to be a very potent way of doing actuation. So you make a material and you write a pneumatic pattern on it, you change temperature or you change stimulus, and then it changes shape. And so one of the big questions is the inverse problem of trying to design the patterns that you can make. And there are two approaches which have been very effective. One is by using piecewise uniform patterns, which I call non-isometric origami, and another trying to do numerics directly. Unfortunately, I don't have the time to describe them, but what I'd like to do is to take a minute to talk about adding another context to this material. So you can take this liquid crystal elastomer, which has this complex behavior it is described, and then try to add to it either in the chain or while making the polymer, a photoactive molecule. So there are these molecules largely, the old one, at one point we only knew azobenzenes, but now with expansions of knowledge in chemistry, we have a large array of these materials. So these molecules absorb a photon and change their shape. And sometimes they can absorb a photon of a different frequency and change back, or by just thermal relaxation, they change back to this original, what is called trans configuration. Now, if you put this into a liquid crystal elastomer, what these molecules do is, depending on their state, they either promote the nematic state or break up the nematic state and promote the isotropic state. So you can use light to undergo this, instead of temperature, to undergo this isotropic to nematic transition. And one of the interesting things is when you stimulate by light, you end up with cyclic behavior. And this was what Ikeda and his collaborators showed by making this kind of machine. But there was actually a newer experiment, which is much simpler, where you have a strip, you're illuminating it with light, and you're seeing this kind of periodic fluttering behavior. So I call this photoelastic flutter in a nod to von Kármán, who of course studied aeroelastic flutter. So I'd like to conclude by kind of explaining this. And so let's try to think what happens when you have photoactuation. You hit it with light. So there's a reaction because of the photons. So this is the number of photons. There's a thermal relaxation back. So the number of activated components behaves using some equation like this. But of course, you're consuming photons. So as the material penetrates a few of your photons, so very often the light decays. So you only actuate a part of it, and that causes spontaneous bending of the material. So you hit it with light and the material bends. And that can be, the bending can be described, these can be averaged, and you obtain some differential equation for this bending in what is called the Snell limit. But once you bend a material, the illumination conditions change, and consequently, the illumination changes. So you have this very interesting combination of light propagation, reaction, and deformation. And this combination, so here's a simple model of that. I have a beam which I've buckled, and I'm going to hit it with light. So this is the beam equations, very simple mechanics equations, which we learn often in our first few years of engineering study. This is the photo part. And all that I'm going to do is to just simulate these with these boundary conditions. And what you find is this kind of photoelastic flutter. You see there's a little bump. The bump moves to the right, then it undergoes an elastic instability, bumps down, and then of course the illumination conditions have completely changed, and therefore again it goes down. You can analyze this in a simple way by just looking at the first Fourier modes of the deformation and the spontaneous curvature. And that's basically this loop here. This is the first Fourier mode of the deformation. This is the first Fourier mode of the spontaneous curvature. You also see that structural instabilities play a very important role. So this is the eigenvalue of the elastic operator. So you see that it undergoes structural instability. So I'll stop here by recalling another work of von Kármán, and that was his analysis of aeroelastic flutter of the Tokamak Narrows Bridge. So, whereas here, the flutter is being caused by optical driving. So I'll conclude with a few thoughts. What I've tried to show you is how one can build in a lot of functionality into materials, and that is part of a larger program which I call Material as a Machine. We are trying to build in a lot of different functionalities. So phase transitions, instabilities play a very important role. What I didn't talk about today is kinetics and failure, but there are challenges in integrating different behaviors in synthesis and design. And importantly, that gives rise to a lot of interesting math problems. I hope I've convinced you that liquid crystals elastomers are very interesting materials. But I'll close by acknowledging the large number of people whom I've had the pleasure of working with in the last few years, and in particular highlight a lot of young researchers. John Biggins, who is a student of Mark Warner, but who spent time at Caltech, and I spent time at Cambridge. Paul Plasinski, who's now at USC. Pierluigi Cesana, who's now in Japan, and current students Tori Lee, Hao Zhu, and Kevin Corner. With that, I'm going to stop. Happy to take questions, and thank you very much once again. Thanks.
Thank you, Kaushik, for the wonderful lecture. I think we do have some time for Q&A. The next lecture won't start until 12. Anyone likes to ask Professor Bhattacharya questions, you can leave your question in Q&A. I think we're getting... We got a message. Okay. So, all right. So maybe I can ask you one, right?
Sure.
Kaushik. So when you're talking about the difficulty of your augmented Lagrangian approach to solve that minimization problem computationally, it's very cute. So you made that into a sort of a nonlinear minimization problem, but it's a local, and then this analytical part will be a linear problem. That's the idea, right?
The idea is the following, that you typically get a nonlinear, nasty second order differential equation you have to solve, right? What you do is using the augmented Lagrangian, you break it up. You forget the nonlinear, the differential part comes from the fact that you have a gradient structure. So you basically forget that it's a gradient, but then you augment, you introduce the compatibility, the gradient structure as a constraint, as a Lagrange multiplier. So when you do that, you obtain a local nonlinear equation. So maybe I can share that equations. Sorry, I have to share it. I have to go back here. So this is what causes the problem. So what you do is you can get, this is the part that I give up. I just call it F, and then introduce a Lagrange multiplier to introduce the gradient structure. But now what happens is you have a local equation, right? And you minimize with respect to F. But then when you come here, you end up with always with a Poisson equation. And there are many nice ways of solving this Poisson equation, right? And this is what you take advantage of. Now, the other part here, which is slightly subtle, is because the solution to this is going to be the right-hand side of the Poisson equation, you really don't have to solve this to some L infinity norm. You only need to solve it for LP norm. So even if there are some points which are not converging, you can actually move forward. So this becomes an extremely powerful numerical method. You can think of this as the constitutive relation. You can think of this as the compatibility equation. And it turns out that the convergence check also has a physical meaning as the equilibrium equation. So all of these things actually work very naturally when you do it this way.
All right, thank you. We do have a couple of other questions now. Kausha, if you can see them.
Yes, I can. If you're with a different scaling rule, do you get a different model? Absolutely. I only talked about the membrane model. And with a membrane model, because I only took this scaling with respect to the thickness, there's a lot of work when you, it turns out that then you can start asking what are the other correctors to it. So you can use the methods developed by Frick, Mueller, and James. The rigidity estimates that they did to obtain higher order corrections to it. And there's a lot of work by Martha Lewicka and her collaborators in doing that. They often call this non-Euclidean elasticity. The other thing you can do is in the kind of models that I described where you also have structural instability, material instabilities, you can actually use the information. One part of the result there from the membrane model is actually you get information about the Young measure, the oscillations, and you can use that to develop corrector theories. And that's something that there are examples of. In one of the examples which I skipped over was where you had a combination of material instability and structural instability. And that's the kind of theory we developed using different scaling rules. So another question from Shankar. Hi, Shankar. So how do you choose the coefficient beta in the augmented Lagrangian? That is really a great question. So in the discrete problem, so I don't know the answer for the continuous problem, but once I discretize in space, but the discrete problem, what you can show is that for beta large enough, you actually have convergence. Now, it turns out that if you choose beta very large, the dual error becomes very large. So you have to play this game of adjusting beta so that the primal and the dual, you balance primal and dual errors. But we have an empirical trick. We basically look at the two errors and we adjust beta on the fly as we iterate. And it would be great to have some theory associated with it, but that's part of what we don't know. But empirically, we basically balance beta between the primal and the dual error. So one more question. Indicate emerging and potential industrial applications of LCEs. So one of the, so very often when you have these emerging materials, it takes a while for applications to come up. One of the immediate applications where there's actually a lot of activity at the moment is a very mundane one, and that's for damping. The fact that you have these phase transitions and you have this microstructure evolution actually gives rise to a very high damping. And so it turns out a very, very, you find that there is a lot of damping in these materials. That's one. So the other one which is emerging is because of the soft behavior, you can take a material and you can make it into a complex shape. So if I take a piece of paper and try to make a complex shape, it begins to wrinkle and becomes miserable. Whereas this material, because of the material instability, can take on very complex shape. The third application, one which I am very interested in, is actually the part which I didn't talk about, and that is about with making actuators. So when you think about the microfluidics, you're using rubber-like materials, but what is often driving it is pneumatics, hydraulics, which is off chip, so far away. So though the microfluidic part is small, the actual driver is large. So I'm very keen on trying to see whether I can use liquid crystal elastomers to make the driver for microfluidics also on chip, because you can integrate this material. So that's 3 examples. But one of the things that you find in these emerging materials fields is that applications you don't think of when you're actually studying the materials, which really often take over. So there's a lot to see.
Great. Well, thank you so much, Kaushik. Thanks, audience, for the questions. I think we're running close to the end of the lecture. Let's congratulate Kaushik once again for the prize and also for giving a wonderful lecture. Thank you all. We'll conclude this lecture as for now. Take care. Bye-bye.
Thank you, Chang. Thank you very much.